Okay, so today we're going to talk about mutual exclusion. This is chapter 2 in your books. We're also going to spend some time visiting an old friend from our basic computing course called Recursion. And I'm going to do this because I think it helps us with the next lecture. So mutual exclusion is, we're going to have a formal problem definition. We have solutions for 2 threads. We have solutions for n threads. And we talk about fair solutions and inherent costs of the things that we're doing. So why is concurrent programming so hard? So the analogy is you're trying to prepare a 7-course banquet by yourself with 1 friend or 27 friends, if you can imagine that. And then before we can talk about programs, we need a language and a way to describe time and concurrency. So imagine trying to organize something with 27 people all having a say. That should be fun. An event A0 of thread A is instantaneous. There are no simultaneous events, so we don't, have to break ties. So it looks kind of like this. We've got this time arrow, and we've got our event happening at this one point in time. A thread A is formally a sequence of events. So on this timeline, we have the sequence of events that constitute the trace of our thread. And this little, this bold-faced arrow here indicates an order. So this says that A0 comes before A1. So the things that could go into thread events are assignment to a shared variable or a local variable or invocation of a method or return from a method or lots of other things. And they're transitions. You can think of each thread as a state machine. So I assume all of you have heard of Turing models of computation. In any event, the point is there is Turing described a way to describe an abstract computational device. And a lot of theoretical work has been laid on top of that description. But there isn't really a special version of the Turing model for parallel computation, which is something that I find kind of interesting. I mean, apparently that kind of thing hasn't, there's been at least one attempt in the literature that I know of to describe such a thing, but it hasn't really attracted the interest of mathematicians and computer scientists the way Turing's definition for a single machine has. Anyway, so states that are in your program include things like a program counter, which is a pointer to the instruction that your program is executing, and then local variables. And there are also system states, object fields, and so on. So in the system state, you have all the threads, right? You have the union of all the thread states. So concurrency looks like this. We've got thread A and thread B, and they're both happening at the same time, and they each have some events. And these events are interleaved, and they're not necessarily independent of each other. So why would that be? So let's suppose that this yellow block represents assignment to a variable A. Okay, we're going to assign the value 3 to variable A. What might happen at this green event that would depend on that?
Reading from A. You
could read a variable. Yes, you could read the variable A. So these, or you could increment it again, any number of things. An interval, which we use a capital A, goes between 2 events. It's a time between 2 events. So this could be the invocation of a method and the return of a method, and this interval could represent the calling of a method. Intervals could overlap in time. So if the beginning and end event contains the beginning event of another, then these events overlap. They could, of course, also be disjoint and not overlap at all. If they don't overlap at all, we can use our bold-faced arrow, and we can say that A naught precedes B naught. If they did overlap, we couldn't say that. We couldn't say either one preceded. So there's our notation. And formally, if the end of event A0 happens before the start of event B0, we can also say it A0 happens before or precedes B0. And it's never true that A precedes itself. And if A precedes B, then it's not true that B precedes A. And if A precedes B and B precedes C, then A does precede C. The funny thing is that A precedes B and B precedes A might both be false, as in the picture, they're overlapping. So this is what's called a partial ordering. So it's irreflective, A never precedes A, antisymmetric, if A precedes B, then B does not precede A, and it's transitive, as we discussed before. So this is the basic rule of partial orders. Total orders are also irreflexive, antisymmetric, and transitive, except that for every distinct A and B, either A precedes B or B precedes A. There's no overlap. So we can have repeated events. So you can have a loop, and then you can have an A0 and an A1 in here. And this could be the beginning of a method call, and this could be the return of a method call, for example. And so the kth occurrence of event A0 would be written like this. And the kth occurrence of interval A0 would be written like this. So the idea, the thing that we are attempting to do is we're trying to make mutex. And we're going to try to use it to make these steps indivisible using locks. And we know what the mutex is supposed to look like. We know how to use one if we have one, right? So we have this interface called lock, and we can call the lock and unlock methods. We've got this acquire and release. So you could do it, and so if you had such a lock, then you could lock it, and you could use the finally block to release no matter what. And in the middle, you have your critical section, where you're doing the thing that you want to do atomically without interruption. And so the critical section IK should be a thread I's kth critical section. And critical section JM should be J's mth execution. Then either this precedes this, CSIK precedes CSJM, or CSJM precedes CSIK. And why can't they overlap? Chris Vasquez, why can't they overlap?
I mean, they're mutually excluded, so.
Yes. So by definition, it makes no sense.
Right.
Okay, so we want something that's deadlock free. So if some thread calls lock and never returns, then other threads must complete lock and unlock calls infinitely often, so that the system as a whole makes progress even if individual threads starve. So if starvation free means if some thread calls lock, it will eventually return, and that means individual threads can make progress. So there are 2-thread and n-thread solutions to creating these locks, and we're going to discuss the 2-thread solutions first because they're easiest and they illustrate the most basic ideas and they can fit on one slide. And then we'll talk about n-thread solutions. So the 2-thread solutions, we're going to use these conventions. We're going to say thread ID.get, and that's going to return either 0 or 1, depending on whether you're thread 0 or thread 1. And then int j will be 1 minus I, so it will be the opposite. If this is 0, or this will be 1. If this is 1, this will be 0. So I is the current thread, and j is the other thread. So here is our first idea at a lock. We have an array of flags, and each thread has its own flag. And then we set our own flag, and then we wait for the other flag to become false. So what do you think of that? Christopher Clark, what do you think of that lock?
Feels fishy, but I'm not totally sure why yet.
Okay, okay. So right, what do you think of that lock?
I mean, I'm not really sure.
Okay. So let me just go again and state what it does, right? What we do is, it's kind of like, you can think of this, right, as the thing we discussed last week with the monsters in the pond, right? We raise our flag by setting it to true, and then we look to see if the other one's flag is raised. Robert John, what do you think?
Not entirely sure, but I feel like there's possible deadlock that may happen. Like flag J may never become false, just stays true.
That's correct. What's going to happen is, if you can just picture this, right, and I think we discussed this last week, if both sides set their flag to true, and then they both enter this while loop, they will both wait forever for the other one to lower it. Okay, so there's a deadlock there. So lock one satisfies mutual exclusion, and that no two threads can actually enter the critical section, but it fails deadlock freedom, right? Concurrent execution can deadlock, so both threads set their flag to true and then both wait for the other. Sequential executions are okay though. If I set my flag to true, the other's flag is false immediately, and I'm good. So here's lock two, and lock two is going to look like this. We're going to we're going to label ourselves as a victim, and that means the other thread can go first. And then we wait for permission. We wait for that, you know, while we're the victim, we wait. Okay, and there's nothing that we need to do to unlock that. So, does anybody have a thought about that one? Can it deadlock? Can we come into a situation like the last time where both threads are waiting for each other?
No.
Right, that can't happen. So that's a good thing, but what can go wrong? Does anybody see what can go wrong? Omar, do you see what can go wrong?
Could they both set themselves as victims? Is that
I'm
possible?
sorry, I couldn't hear you.
Could they both possibly set themselves as victims?
Well, if they did, right, then the last one, then whichever one set themselves to victim as first would eventually succeed, wouldn't they?
Right.
You could have a situation where mutual exclusion is broken because if a third thread calls lock, then it unlocks the second one, right, when the first one may not have been out of the critical area.
Good. That is a good observation. However, we did specify that we were restricting ourselves to two threads. But that is a good observation. This is supposed to be a lock that only works for two threads, however. Alexander, do you see a problem with this lock?
I'm imagining what if neither of them would have set the other as a victim? I don't know.
Well, neither does set the other as a victim. Each one only sets itself as the victim, right? Because I is always the current thread.
Yeah.
You get starvation if no second thread comes along.
Correct. Who said that?
Okay. Chris.
All right, thank you. Yes, that's the problem is if the other thread doesn't come along, then it's starved. So lock 2 satisfies mutual exclusion, but it's got the problem with the sequential execution deadlocks. The concurrent one does not. So now we're going to look at Peterson's algorithm. And in Peterson's algorithm, we set we do both things. We combine lock 1 and lock 2. We announce that we're interested with the flag. Then we set ourselves to be the victim. And then while the other's flag is true and we're the victim, we wait. Okay, and then when we want to unlock, we set our flag to false. So this is deadlock free. And the thread is only blocked at the while loop and only if the other's flag is true and only if we're the victim. Solo, the other flag is false. Both, one or the other is not the victim. So it's going to work. So it's starvation free. Thread I is blocked only if J repeatedly re-enters so that flag J is true and victim I is equal to I. When J re-enters, it sets its victim to J, so I gets in. So does that make sense to everyone? I'll get you all to start speaking to me yet. It'll happen. I guess it's easier when you're live in a room, but I'll get you there. Okay, so the filter algorithm for n threads looks like this. There are n-1 waiting threads called levels, okay? And at each level, at least one enters the level, at least one is blocked if many try, and only one thread is going to make it through. So the filter lock, we're going to have an array of levels and an array of victims, and we're going to instantiate the filter with a size that's going to fill both of those. And then what we're going to do is we're going to set our levels to 0 initially. Eventually, what we're going to do is we're going to have the threads make progress. So if I put a 4 in the level array at position 2, that means thread 2 is at level 4 of the lock. Okay, to do the lock, what we're going to do is we're going to iterate from 1 to n. We're going to set the level to the one that we want to enter. And then we're going to set ourselves to we're going to set the victim at that level to us, right? And then we have this pseudocode here that says for every, while there exists a k not equal to I, and a level k greater than L, and victim L equal I, we wait. Okay, so this is going to replicate the Peterson lock L times, essentially. You have to make progress through each of the levels. So we're going to go, well, okay, we're going to go one level at a time, announce our intention to enter the level, and then we're going to give priority to anyone but ourselves, and then we do this existence loop. And thread enters level L when it completes the loop. And so we start at level L, and at most n-L threads enter level L, and mutual exclusion at level is at level L equal n-1. So if you make it all the way through, you get there. And so you can do this with with all these threads, and the filter lock satisfies the properties just like the Peterson algorithm at any level, so no one starves. But what about fairness? Threads can be overtaken by others. So we can do n threads this way. We can have an n thread Peterson lock this way, but we want we want things to be fair. We don't want a thread to be overtaken too often. So if thread A starts before B, then then A shouldn't enter before B. But what does it mean to start? So we're going to adjust some definitions. And we're going to divide the lock into two parts. There's a doorway interval written DA, and this always finishes in finite steps, and a waiting interval written WA that may take unbounded steps. I'm just going to point out that this is terminology that I will expect you to know, okay? For threads A and B, if doorway A precedes doorway B, if doorway A for thread K precedes doorway B for thread J, then A's kth doorway precedes B's jth doorway. And so the critical section of A has to precede the critical section for B. At A's kth critical section precedes B's critical section. So the idea is that B cannot overtake A because the doorway for A went first. So the filter lock satisfies the properties that no one starves, but it has very weak fairness, and you can be overtaken an arbitrary number of times. And you can argue that that's pretty lame. The bakery algorithm provides a first come, first served. And how does that work? In the bakery algorithm, we take a number and we wait until the lower numbers have been served. So this is like, you know, a deli, for example, if you've gone to a place like that. You take a little paper counter and you wait for your number to be called. And what we're going to do is we're going to make a lexicographic order out of a tuple, out of a set of values. So the way this works is, right, if A is greater than B, then AI is greater than BJ. But if A and B are equal, then we check I and J. And if I is greater than J, then AI is greater than BJ. Okay? So that's the way that works. So the bakery lock, we're going to have a Boolean array of flags and a label array of labels, which, and what we're going to do is we're going to instantiate the Booleans and the labels. And then we're going to take a look. Okay. All right. So that was, sorry. Then we're going to look at the algorithm itself. So the lock algorithm, we're going to set the flag to true, and then for the label, we're going to find the maximum of all the other labels, and then we're going to add 1 to it. Okay, and that's the doorway. So the flag says I'm interested. This takes the next number. Okay, but it could be the same number as some other thread, right? There's nothing that really stops, you know, two threads from executing this step at the same time. And then I do then I go and I look, and if I find someone that's interested, and that person has a label I, comma I greater than my label K, comma K, right? Then even though the labels might be equal, that pair of things won't be equal, right? Which includes the thread number. And so there's never going to be a case where these two things are equal, right? Unless I is equal to K, and we're not gonna include that case. It occurs to me that's an error on this slide. It should say K not equal to I here. Okay, so, and the unlock algorithm is just setting your flag to false, saying you're not interested. And so the labels are always increasing. And there's always one thread with the earliest label, and ties are impossible. And I think I've already told you why. So this gives you a first come, first served situation. If the doorway of A precedes the doorway of B, then A's label is smaller, okay? And that means it's going to go first. And if B sees a smaller label for A, if B sees a smaller label for A is locked out while the flag A is true. So hopefully this all makes sense to you. Does it not make sense to anyone? Does anyone have a question? remember, I want you all to ask questions. Suppose A and B enter the critical section together, okay? And suppose A has the earlier label. When B entered it, it must have seen either flag A is false or label A is greater than label B. And either is impossible. Oh, so we're trying to prove mutual exclusion here. I'm sorry. So we're gonna start with a thing we believe is false, that A and B enter the critical section together, and we're going to suppose that A has the earlier label because it either has it earlier or later, and without loss of generality, we can say it's earlier. So when B entered it, it must have seen that flag A is false or label A was greater than B, and both are impossible because that's excluded by the code. So it will work. All right, and that is the basics of mutual exclusion, which we covered in half an hour, unsurprisingly to me anyway. Now I'm going to come up with some homework for you about this, and I don't have the complete homework ready at the moment, but I will tell you that I expect to see you implement and test a bakery and filter lock. So what you've got here is you've got something that in these slides, and in the book, what you've got are things that are pseudocode. Things are kind of wrong in details, or syntax that doesn't exist. There is no there exists a K statement in Java, for example. So I'd like to see you actually code that and get it working. All right, let me exit slides. First, any questions on the slides? Okay, don't count on me seeing, Christopher, don't count on me seeing chat messages. While I'm sharing, it's very hard to get things up in Zoom. Just please unmute and talk to me. So you said something about shared memory at some point. I don't know when that was or how that worked. All right, so one of the things I'd like to show you is
Quick question.
Yes,
If we raised our hands on Zoom, would you be able to see it?
Unlikely. While I've got the presenter mode up, it's hard to get the other screens up and watch them.
Ah, okay.
Really, I just need you to ask. I just need you to unmute. Just pretend we're really in a classroom.
All right.
All right, so what I've got here is a website that you can go to, and you can type Java code in there, right? And then you can execute it with this button here, and it prints "Hello World" or whatever you want to do. And you can put any, if you don't have Java installed on your local machine, you can just use this tutorials point compile Java online to play with code and try things out. However, I think it's kind of nicer to have something actually installed on your machine. All right, so what I'd like to do next is I'd like to talk to you a bit about a blast from your past, recursion. So the reason I want to talk to you about recursion is because you may not have realized one of the nifty things about it. share my screen again. All right, so let's see, which is the one I would like to have a simple one first, and I don't really have a simple one. So I'm going to say I'm going to create a class called group sum 0. And the way this is going to work I want to create a find group. What I want to do is I want to add together. I want to find if there's a set of values that I can add together that will equal the sum. Okay, and so I want to be able to say test, and then I want to say, well, let's say assert find group I want to assert that that's true, right? But I want to assert that, I don't know. And so the question is, how do I write this method? And the way that you do it, right, is with recursion. So what you can say is you can say return find group values 0. And you can say boolean res find group values pos plus 1 sum minus val. Okay, and you can say if res return true. Otherwise, what you're going to do is you're going to return find group values pos plus 1 sum, and I think that's right. Let's try it out. Well, it's obviously got syntax errors. Oh, well, that's silly. I forgot to put a type on pos. And
You misspelled return.
I'm sorry, I misspelled return. Oh, ret run.
Mm-hmm. Also, I'm a little confused about what you have for assert on line 21 and 22. It seems like you're missing a curly brace on both of them. I'm not sure where that goes.
Hold on. It should be a parentheses.
Oh, okay.
All right, so now that's guaranteed to succeed because I didn't enable insertions. There we go. Okay, so now this code might not seem wonderful to you, but it is actually kind of wonderful because what it's allowing me to do is it's allowing me to explore all possible ways of including of each of the values. So this is, you know, deciding this is going to, for each value in this array, it's going to either include it or not, right? And by just doing this little recursive step, I can search all the possibilities of using 1 or not using 1, using 3 or not using 3, using 5 or not using 5, okay? And so I can take this and I can write a loop. Let's see what it is. Picking this at random, really. I don't know the percent for a Boolean, it turns out. We'll see what this, I'll just try this and see if it works. Yeah, format specifier B is no good. I'm going to try, I will actually look something up if, oh, okay, so what this is basically showing us is for the set of integers that I picked, right? Everything up to 18 is going to have something that works. And that's probably because I included things like 1, 3, and 2. So if I made this 11 and 20, right, then oh, I've changed the wrong thing. Dopey me. Okay, now I've got some gaps in here, right? Now, the way I've written it, 0 is always going to be true. That just says if you don't include any of them, you sort of have 0. And that's a detail that I could worry about or not. Does anybody have any questions about that particular recursion problem? Okay, so what we're going to do is we're going to explore all the different ways, a bunch of different ways that we can permute that problem, we can make it different. So here's group sum 1. And the idea behind this problem is that if we want to know if some combination of integers adds up to the target value, but if we use the integer at position I, then we can't use the next one, the one at I plus 1. And so that one looks very similar to the one that we did before, right? What's going to happen, though, we're going to do our group sum. And when we include our value by subtracting it, right, we're going to put our position as +2 instead of +1, because we have to skip the next one if we do that. And that way, we only look at +1 if using the current value fails. All right, and that small change allowed us to take this variation into account. Okay, so the point is that all these things remain quite simple. I think this is the one I just did by hand. Oh, group collect is what I'm looking for. Now here's a variation on the problem that we had. And what this is going to do that's different is it's going to fill in a list of integers. In addition to returning that Boolean value, it's going to return the list of values that made that sum. So the way that's going to work is if I call this first one where I subtract the value, okay, then if that initial res is true, then I'm going to add the value to the list. So only if I know from doing the whole recursion that that value will work, do I add it onto the list. And so what this is able to do, right, is I can go in here and I can run this one, and I know I can get 2 and 5 back. So all right, so in this one, it's going to show me 5 and 2. This one is going to show me false, and there's going to be an empty list. And this one where I have 5, 1, 1, it's going to show me that I can how to make 7. And again, with this one, it's going to show me how to make 7. Okay, so if you want to, you can include this mutable state in your call to your recursive method, and you can collect the values or collect information about the search you're doing. But the point is, again, recursion is a good way of taking a problem and searching for all possibilities. It makes the notion of searching for all possibilities a little more straightforward. Questions? Now, come on, I know somebody has a question about something we've said today. I know you're probably just being shy.
How come the start +2 one on group sum has to be start +2?
So this one you mean?
Yeah.
So up here, if we use the value at position I, then we can't use the next one.
Oh, okay, okay. Okay.
Yeah, so very often, I realize when people ask questions, very often it's going to be because they didn't quite hear something. But that's okay. I mean, that's what, you know, sometimes you miss things in lectures. I know that I myself frequently will have little blank spots when I'm trying to listen to people because my mind wanders now and then. They say something and it makes me think of something else, and then I miss the next thing. All right, so let's try a little interactive exercise, all right? What I want you to do is to take a list of words. So take some list of words. It can be arbitrary. Right? And then what I want you to do is I want you to write a program that says, called make word. So it takes these words in some given set of letters and determines can some combination of the letters make one of the words. So make word ES33J GG or GFG would be true. Might no, it should return egg. Well, first let's go for true. Okay, that should be true, but say this should be false, right? Because that set of letters there can make the word eggs, but if I only have one G, then it's not going to work. Okay, I can't make the word eggs. And make words C HISF should be true because that can make fish. Okay? So do you think you can all write a program that will do that? All right, somebody say something. You say, I'm terrified. Say, oh yeah, I can do that, no problem. I just want to hear some feedback.
I'm a little rusty, but I think eventually I can make that program.
Okay. So let's start with words. How am I going to represent that in Java?
Array of strings.
What's that?
An array of strings.
It could be an array of strings. What else could it be?
A list of strings.
A list of strings. What else?
Two-dimensional character array.
Right.
Which is basically just an array of strings.
Right, but let's think about the Java util. What's in Java util? Is anybody familiar with that? I mean, array of strings or a list of strings are perfectly fine. Don't get me wrong.
A char sequence.
That's a more abstract string. What I'm getting at is a set. Are people familiar with a set?
Yeah.
So a set is kind of nice because what I can do is I can say, set contains, right? And that will tell me if one of those words is actually in the set. So rather than writing a loop and checking each thing individually, I can just say contains. It's already got a method for that. And it's optimized in certain ways. So what I'm going to do is static set string words equal new hash set. And then I'm going to words.add bat. Words.add fish. Words.add walrus. Words.add eggs. Okay, so this will create a static variable that is like a global variable named words. And then I can just add the words in with the add method, and I can use the contains method to see, if that word is contained in the set. So the idea behind a set, right, is all the members are unique. So I can't have the same word in it twice. It's just a little optimization for me. So now set string words, and then string letters. Okay, so that's my method signature. So does anybody have a thought about what that method should contain?
My naive implementation would just be to permute the input character string all the way, and each time check whether or not it matches one of the words in the word set.
Okay, so so the thing with permuting, okay, is you need to remember that a subset of the letters could be in the words, right? So if we simply permute it, we'll keep all the letters, right?
Right. So you'd start with, yeah, one letter. You take each letter individually and then create longer and longer strings until you're using all the letters in the set.
Right. So your description of how to do this is essentially correct. Okay. The question is the details. So let's go back to these aren't good examples for what I want to say. So, oh wait, yeah, they are. Hold on. All right, so I didn't actually set this up this way, but let me just change this example. So in my group sum 0, right, what I'm going to have, actually, let me go to group sum 0. I think I did it right there. Yes, okay. So this is the thing I meant to use. So what I did is I had a find group, I had values and a sum. Now, in addition to that, that values and sum, right, I needed a position within the values that I was checking, right? I needed to iterate through the values in that group. And so what I did is I just overloaded find group to give myself that starting position of 0, because I know that every time I'm going to want to start at 0 and go to the end, right? So I just added that in there by overloading my method and adding a field. Okay, so makeword.java is going to be like that as well. And so what do you think? What do you think I'm going to put here? And somebody other than Christopher Clark can answer. Given what I've just said, what kind of thing do you think I'm going to put here?
Well, are we not going to need an overloaded method that has like an in parameter?
Yeah, we're going to need that. So let's say 0, because we're going to start with 0 and letters. Okay, so that's just, puts off the actual work. Okay, so what we need to do is we need to know, well, first of all, is that the only thing that we need is the position? Is that the only thing we need? So let's picture how this is going to work, right? As Christopher described it to us. He said what we're going to do is we're going to go through each letter in turn and try to add it to a word, right? And look at all the different permutations of that set of letters, and see if it fits. So do you think the only thing we need here is a position? Or do we want something else?
Do we need to keep track of the words we make in the permutations?
So I was thinking that we would keep track of a word, right?
Yeah.
So I was thinking that we would have some word that's in progress that would initially be our working word that we're going to try to add a letter to. Okay. All right. So the easiest thing we could do is try to add the letter at the end, but that's not good enough. So what do we need? What do we need to check inside our make word? We've got a working set of letters. We're going to add the letter from the letters set at position pos, and then we're going to look at all permutations of that additional word with that additional letter added. And we want to check to see if it's in our set of words, right? Is that correct? Is it not correct? Am I incomprehensible? I like to think I'm comprehensible. Let's back up a step. What do we need? Going back to your 1351 roots, what does every recursive method need?
An exit condition.
An exit condition. Very good. Okay, so Alexander Tisdale, I think you've answered enough. I'm pleased with that. You don't have to keep going. Can somebody tell me what the exit condition might be? So for people who have arrived late, we have already gone through the slides relating to creating a mutex, so you can review those. What I'm doing right now is I'm just doing a reminder of recursion because I think it's going to be helpful in the next lecture. And I was just working through some code examples because I want you all to be able to code. And in this particular example, what we're attempting to do is we're attempting to determine if we're trying to write a method called makeWord, which it determines if there is some way to put the letters that we have in the input string together to make one of the words in the set of words. Arbitrarily, I've made a set of words like this, and what we're going to do is we're going to call it, as I say, like this, make words with a value like this. So if I call it with ES33GFG, I should get true, and ES33GF, I should get false because I only have one G in there. And if I call HISF, it should be true because I can make the word fish with it. So we know that we need an exit condition for this function. What should the exit condition? What possible exit condition or conditions should there be for this recursive function? Well, I need to know if I found the word, right? So we could say if words dot contains working, then we return true. What's a situation where we would return false?
When we're not able to find all the letters in the word.
Right. But how do we know? How do we codify that? Omar, do you have an idea of how we would codify that?
I'm not sure.
Okay. So let's sort of think about how this is going to work. We're going to say somehow new working equals working plus letters dot care at pos, right? Because we want to do if we want to make some new working string from our existing one plus the next newest letter in the list, right? And then we want to say, if make words pos plus one new working letters return true. Okay. So given that we're going to do something roughly like that, what's the condition for false?
If there aren't any characters left.
Right, and how do I write that? Lyndon, how do I know if there aren't any characters left?
If position plus one is greater than the size of,
Right.
yeah.
So the way I'm going to write it is,
Yeah.
okay, so I've written this new working equal working plus letters. But that isn't quite right, is it? Because I don't always get to add the letter at the end. It could go anywhere, couldn't it? So I need to be able to add that letter to any position. So if I have, for example, imagine that I have the string FSH, right? And I want to add the I. What I want to do is I want to try out IFSH, then FISH, then FSIH, and FSHI, right? I want to be able to try out all of those possibilities, correct?
Yeah.
So So what I want to do is I want to be able to combine a string and a character at a position. And that position can be 0 if I want it in the front, or it can be, you know, the length of string A if I want to put it at the end, right? And so I can write that straightforwardly. Right, I can do that, and then I can say sb.append b, and I can say for int I equal n, I less than a.length. And then I can return sb.toString. Okay, now, to do this part, I now need a loop. Starts with 0 and goes up to what? So if my word were if my working word were FSH, right? What values would I need I to go over? 0. And what else?
The length of the string.
The length of the string, which is
0, 1, 2, 3, so 4.
well, 0, 1, 2, 3. This string is 0, 1, 2, 3. So I is less than or equal to working length. All right. So now, new working is going to be combine working letters caret pause and I. Okay. And then we're going to say if make word at as I plus 1 new working and letters, we're going to return true. And if we go all the way through, we're going to return false. So hopefully this works. Now we don't know that it works yet. We don't actually even know that it compiles. Let's try and find out if it does. Okay, I forgot a semicolon. So I forgot to give new working a type. Silly me. And I forgot to make combine a set. All right. Now let's do our test. Assert, make word, words. What did we say? We said this one. We have to enable assertions. And, oh, hold on. Okay, we got assertion error. Unfortunate. So we've got something wrong, because that should have worked. Eggs is in our word list. Yes, eggs is in our word list, and we didn't find it. So let's just take a look. I like to put a print statement here. Let's just see what goes on in this variable. You know, this is the problem with programming in multiple languages, is you kind of forget, you kind of mix things up. So that's an awful lot of output. Let's just take a look at this. Ah, do you see what I did wrong? Who sees what I did wrong? The string eggs doesn't occur here. Why doesn't it occur?
It's just adding the characters to the beginning of the string.
It's not taking into account the situation where I don't use the character, is it?
No.
How do I do that? How do I change this? How do I fix it so that it takes that situation into account? Somebody help me. All right, so what I've done, right, I've tried adding the letter in all different ways to create a new working, and then I've checked with the new working. What I didn't check was without the letter. How do I check to not have the letter? I want to move on to the next character, but I don't want to. I don't want to add the current character to my word. What do I do?
Make word is where, oh, you could do the contains check before adding the character.
I am doing the contains check before adding the character. I'm doing it every time I enter the method. I need to do an additional check of some kind. How do I do that? So this is checking. This is checking with the new character added, right? In every possible place. How do I check not adding the character?
Would you do it in the original make word call?
No, I have to do it for each step of the process, right? So for each letter in the string of letters, I have to one of the possibilities I have to check is, in addition to adding it to every position within the working word, I have to try just not adding it. How do I try not adding it? So here I use the combine method to add this character to the working set to create a new working. How do I check not doing that? Right, this is the actual check. This is where I check whether that new working word is in the set. How do I check not doing that?
Can you do that if statement? Can you just add an or to like the old working and the new working?
Well, I could add an or, but in recursion, what I need to do is I need to check something else. So let's try this, okay? Make words. What should I put for the position? Pos +1. If I don't want to include the word, what do I put? If I don't want to include the letter, what do I put?
Working.
Working. and then letters. Okay, so this is going to check going on to the next letter without changing working, right? It's just one more recursive call in the set of recursive calls. And now it works. At least it worked for the first test. Let's just try the other ones. So that worked. Okay, and let's try this one. All right, so the idea is, and the thing that I want you to take away from this second part of the lecture is I just wanted to bring back recursion into the forefront of your thinking. And I wanted you to see that one of the things you can use recursion for very effectively is for searching all possibilities of something. Okay, and you can use it to compute permutations. You can just use it to compute permutations. That's a standard example. But I think that looking at these, find the number of, find the set of integers that add up to the certain value and so on, allows you to see how you can do searches with it, right? There are all kinds of variations on these search problems that you can figure out. And, I'd like you to just try a few out to see if you can figure out how to fit your brain into this, into knowing how to use recursion to do a search for an answer. Okay. Are there any final questions on what we've covered today? For the rest of you, please be like Sarait and Christopher and have pictures of yourselves next to your names. You can set them in your settings. I want to see your smiling faces or your frowning faces or whatever. I just want to see your faces. So please do that. All right. Since there are no questions, I will conclude at this point. Thank you all for coming.